Okay. And maybe we should wait just 1 or 2 minutes more, if that's fine.
So I have 30 minutes or 40 minutes for my presentation.
So, Cicero, what do you think?
Yeah, we have 1 hour and a half for the whole seminar. I think that 40 minutes is the maximum, and I think, yeah, but it's up to you if you can, if you feel more comfortable with 30 minutes, you can do 30 minutes or 40 minutes. So
no problem. Okay, sounds good.
Yeah, okay.
I just spent some time in Sao Paulo a few days ago.
Yeah. Was your first time in Sao Paulo?
No, not my first time, no. But I enjoyed this greatly. This was a JBS organized meeting, a methane conference, and I was surprised how many producers were there. So this seems to be a topic that's really at the heart of many in Brazil's agricultural sector.
Yeah. Some colleagues of us in our group were there, and yeah. So also Professor Assad did a presentation in the.
Oh yes, I remember. Yes. Mm-hmm.
Yeah. Professor Assad's here also.
Great. Oh yeah, there he is. Hello.
Yeah, hello. Great to be here.
Small world. It's
again.
a small world. In 3 days, I'll be in South America again. I'll be in Paraguay and Argentina. So
Fantastic.
For a week. I spend more time in South America than in North America these days.
So do you, by any chance, since you're nearby, would have the chance to actually come to São Paulo again?
Not during this trip, definitely not. No, my agenda is totally packed between Argentina and Paraguay. They sent me the agenda today, and I don't know if I have time to breathe.
All right. So I think we should already get starting. Would that be okay, Cicero?
Yeah. We can start. Let's go.
All right. So let me just make a quick introduction, and just for the purpose of some preliminary remarks. So thanks a lot, Professor Mitloehner, for your generosity to join us and share your ideas with us. So here we have launched the Observatório of Bioeconomy at Getúlio Vargas Foundation in November. We are a multidisciplinary research and policy center. We gather researchers and ideas coming from different disciplines and schools, especially economics, law, and land sciences. And one of the main goals of the observatory is to support the country in its task of fostering the green transition, taking into account especially this difficulty, this challenge of decarbonization, but not only that. We work on different fields, so we are very much concerned with deforestation in the Amazon. We have a lot of interest in agriculture and livestock production. We also work with the energy transition and debates that are taking place in the country in this area. Some of our recent publications and research, they deal with questions such as the organization of the Brazilian carbon market, challenges and strategies to mitigate emissions in agriculture and livestock. And we are very much excited with the perspectives, and we are very much interested in building this network and engaging more powerfully, intellectually as we can, not only in Brazil with figures in government and in private sector, but also with global institutions and smart and interesting people like you. I have the honor to quickly introduce Professor Frank Mitloehner. He's the professor and air quality extension specialist at the UC Davis. He's based at the Animal Science School, if I'm not wrong. His research is focus in two main areas: air quality research related to livestock production, and environmental physiology research, focusing on the effects of air emissions and animal health. And I first got to know Professor Frank Mitloehner a few years ago, reading some public discussions on a United Nations report that actually claimed that the livestock's contribution to climate change was significantly higher than the whole transport sector. And he very candidly and smartly questioned that report publicized by the United Nations Food and Agriculture Organization, which a few years later came to admit that there were some incongruencies or some imprecision in the methodology that was actually adopted in the organization of that report. And since then, I had the privilege to follow some of his constant engagements in the public media and in public discussions, very often calling our attention to the particularities and the relevance of the livestock production and how we should be somehow more careful and more, I think that's the word, in the way we actually measure and quantify emissions coming from agriculture in general and livestock production in particular. So that's all I have to say. And I would like once again to thank very much Professor Mitloehner for sharing his time and his ideas with us. So he will make a quick presentation of his ideas and research. And after that, Cicero, who is a member of the observatory, will also talk a little bit about a research that has been co-led by Professor Eduardo Assad. And he'll share some of the quick results, some of the main results of this research. And then we have the chance to open and talk a little bit more about the ideas. So Professor Mitloehner, the floor is yours. Thanks a lot.
Thank you very much. I appreciate the invitation, and I'm really happy to meet with you here today about livestock and climate, a topic that is certainly hot here in the United States, even hotter in, let's say, European countries. But as I just experienced when visiting Brazil a few days ago, it is also of great importance to the Brazilian economy, to the Brazilian people. And so I want to be very clear insofar that I do not downplay the importance livestock has on climate. I will not downplay the importance of methane. Sometimes people think that what I say means that methane doesn't matter. It doesn't mean that. Methane does matter. But it is very important that particularly methane receives the correct attention it deserves, because methane is different from other gases, and you will see that during my seminar. So I think it's very important that we get this narrative around greenhouse gases from livestock correct, okay? And that's what I'm striving for. As Dr. Vargas just pointed out, I am on social media. I never thought I would, but 2 years ago I started it, and the GHG Guru is my handle. There's a lot going on this platform and others. I'm also the director of the CLEAR Center. If you go to clear.ucdavis.edu, you will find a lot of explainers, blogs, YouTube, seminars, and so on presented to you. Really quickly, I don't think this audience here requires this kind of background because you have it, but the reason why we are concerned about greenhouse gases is because they are believed to trap heat from the sun. What you see here is the sun radiating down solar beams to the surface of the earth. Normally those would be reflected back into space if they weren't the so-called greenhouse gases that effectively form a blanket over our atmosphere, retaining heat back in the atmosphere. So this is a critical function these greenhouse gases have. Without them, life on Earth would be too cold. So we need greenhouse gases. But the problem is we are producing too many of them, and that means this blanket is getting too thick, retaining too much heat in our atmosphere, leading to the global warming effect. So while most climate scientists will agree that carbon dioxide is the main greenhouse gas stemming from the combustion of fossil fuels, which is the burning of oil, coal, and gas, the critics of animal agriculture focus on methane and say, no, it's methane that we need to concentrate on because methane is more potent than CO2 in trapping heat from the sun. When greenhouse gases are compared to one another, a so-called matrix is used that's called global warming potential. And most often the GWP, global warming potential 100, is being used, which expresses the potential of of these gases to trap heat over a period of 100 years. And you see here that these numbers for GWP 100 for the different greenhouse gases vary. For CO2, which is the normalizing one, it's 1. For methane, it's 28. For nitrous oxide, 265. These values have changed over time, but currently you see either 28 or you see 34 as a factor for the potential of this gas to trap heat from the sun. So it's what this really means is that a ton of methane equals 28 tons of CO2e or CO2 equivalent units. This GWP 100 is the way that most governments in the world quantify greenhouse gases today. And it started being used in 1990 when the Kyoto Climate Accord was first created. And this GWP 100 might work for nitrous oxide. It also works for methane if methane goes up in a given area. Okay, so if methane emissions increase over time, then there's not a lot to criticize. But in many regions of the world, methane is not going up, but it's either held constant or it's decreasing. And when that happens, then GWP 100 shows some significant deficiencies that I will point out in the next few slides. Before I do that, I want to talk about something that is not as intuitive as people think, namely that for methane, and in contrast to CO2 and nitrous oxide, for methane, there is actually a budget because they are not just sources of methane, but they are also sinks for methane. So on the left side of this slide, you see the global methane budget. And here first the sources, including fossil fuel production and use on the left, then comes agriculture and waste, biomass burning, wetlands, and so on. Amounting to what you see in the first half bubble, 558 teragrams of methane produced from these various sources. This, unfortunately, is where much of the discussion around methane ends, when indeed it shouldn't end because there's a right side of this budget. And the right side shows you see there are two arrows pointing down. One says sink from chemical reactions in the atmosphere, and the other one says sink in soils. These two sinks amount to a whopping 548 teragrams, which is the second half bubble to the right in white. So if you want to know what is the global net contribution of all anthropogenic activities, then it's not 558, it is 10 because you have to subtract the sinks from the sources. Still a number that we seek to reduce, but certainly one that's grossly different from just focusing on the sources. So keep in mind, methane is not just produced, methane is also destroyed. And if you look at the largest arrow pointing down, it says sink from chemical reactions in the atmosphere. What does that mean? That means that there are molecules in the air, they are referred to as hydroxyl oxidants. And these hydroxyl oxidants are radicals that when getting in contact with a methane molecule, destroy that methane molecule and convert it into water and CO2. So because of this very large activity there in the atmosphere, this oxidation, because of that, methane is grossly different from other greenhouse gases. And this very step here leads to the situation where methane has a very short lifespan. You see here the half-life of greenhouse gases. You see that CO2 has a very long half-life of 1,000 years, meaning if you drive your car today, you burn gas and the CO2 that comes out of the tailpipe will stay in the atmosphere for approximately 1,000 years. The same is true for nitrous oxide, not quite as long-lived, but it's also a long-lived climate pollutant. So not just is nitrous oxide very potent as a greenhouse gas, I showed it on the earlier slide, but it's long-lived. So that's a double problem it has. Methane is different because of the fact that methane is not just produced, but also destroyed. It has a short lifespan of approximately 1 decade, 10 to 12 years. So it's important to know methane is different from the other greenhouse gases. It's not just produced, it's also destroyed. And that fact reduces its lifetime in the atmosphere. So then the next question becomes, where does the carbon in the methane that comes out of the front end or from the manure of cattle and other livestock, where does that carbon come from? And is this carbon that cattle produce additional to our atmosphere? Now comes something really important. The Paris Climate Accord does not have an emissions goal of reducing additional carbon emissions by so and so many million metric tons. But instead, the Paris Climate Accord has a temperature goal of not adding additional warming beyond 2 degrees centigrade. That is the goal of the Paris Climate Accord. So that means in order to achieve the goal of not causing additional warming, we need to have a goal of not putting additional carbon into the atmosphere. So does livestock, every time that these animals belch or produce manure, produce additional carbon that leads to additional warming? Well, in order to answer that question, let's take a look at the so-called biogenic carbon cycle, which is the cycle that starts with photosynthesis of plants. We all know photosynthesis is the process by which plants need sunlight, water, and a source of carbon. And the carbon they need, they receive from the atmosphere in the form of atmospheric CO2. That CO2 then, that CO2 carbon is taken on by the plants, becomes either cellulose or starch. Animal comes along and eats the carbohydrates contained in those forages. And then in the rumen, those carbohydrates are converted into other compounds. One unintended consequence of ruminant digestion is enteric fermentation, by which enteric emissions are produced, and here in particular methane. The question now is this carbon in the methane, the C in the CH4, new and additional to the atmosphere? Is this carbon in the methane new and additional to the atmosphere? And the answer to that is that a constant herd of cattle produces roughly a constant amount of methane. And the carbon contained in that methane is not new and additional, but it is recycled carbon. It started in the atmosphere in the form of CO2. So this carbon in the methane is not new, it's recycled. Yes, this methane is a potent greenhouse gas as long as it's in the atmosphere, but a constant source of cattle and livestock produces a constant amount of methane, and that produces a constant amount of warming. Why constant? Constant because methane is not just produced, but methane is also destroyed almost at equal rates. A constant source of methane produces constant warming, and that's really important to understand. What happens to this methane is it's destroyed through hydroxyl oxidation after approximately a decade and converted back into atmospheric CO2. It goes into the pool of atmospheric CO2 from which, for example, plants pull carbon again for photosynthesis, but also, of course, it goes into just the atmosphere in general. So the biogenic carbon cycle is one where atmospheric carbon goes into plant carbon, cattle consume that plant carbon, make methane. The methane stays in the atmosphere for 10 years and is then converted back to where it came from. What results from the oxidation of that methane, however, is not new and additional carbon. This CO2 is not new and additional, but it is recycled. It used to be CO2 before this 10-year cycle. So how is this biogenic carbon cycle similar or different from other sources of carbon? For example, the number one being fossil fuel derived greenhouse gases. First of all, what are fossil fuels? These are ancient plants like forests and animals such as dinosaurs that died and decayed and fossilized hundreds of millions of years ago. It's the entire biomass that lived on Earth a long, long time ago that died, decayed, fossilized, and accumulated underground. And over the last 70 years, 70, humans started to take that carbon out of the ground. And what did we do with it? We burned it. So where's that carbon that was in the ground for so long? Where's that carbon now after burning it with cars, trucks, trains, planes, ships? It's now in the atmosphere. Every time we burn that carbon, we add new and additional CO2 to the atmosphere. Okay? And by the way, if methane comes out while drilling, pumping, and so on, the fossil fuels out of the ground, if methane comes out from these sources, that is also new and additional methane. That is not a short cycled methane. This is new and additional methane from the fossil fuel sector. So to contrast these two, on the fossil fuel side, we have ancient carbon that was in the ground for a long time. We take it out of the ground, we burn it, and we add new additional CO2 to the atmosphere. On the livestock side, however, we have atmospheric CO2 that makes it during photosynthesis into plants, first above ground, then the majority of the carbon goes below ground, first into the roots, and then due to microbial actions in the soil, into the soil where it's locked away, a process called soil carbon sequestration. I think this is a process particularly of interest in a place like Brazil, where you have a lot of grazing land and where you need to know how much your lands sequester, how much your lands trap. Of course, you have the added complication in a place like Brazil, where you not just have land as a sink for carbon because you have grazing lands, but you also have land as a source if you take vegetation off, for example, by burning forests or by and so forth. So it's very important to get a good feel for Brazilian land use as to what the trade-off is between soil carbon sequestration in general on the one side, and then also carbon release on the other, and the taking away of carbon sinks. So now cattle come along, eat above ground vegetation, belch out some methane. That methane, however, will become CO2 again. So we have the fossil carbon on the one side, on the left side, and then we have the biogenic carbon on the right side. The one is a one-way street, the other one is a short-lived cycle. I hope everybody understands why these two are quite different indeed. So now colleagues of ours from Oxford University some time ago said, well, the way we currently quantifying methane and its impact on warming is wrong, because we are using GWP 100, which accounts only for the production, but not the destruction of this gas. And so it also, this GWP 100 doesn't actually describe the warming caused by methane, but it only converts methane into CO2 equivalent units. So they said this is wrong. First of all, the old unit GWP 100 is totally overestimating the impact of constant sources of methane by a factor of 4. It's overestimating the impact of constant sources of methane on warming by a factor of 4. Now you really have to let that sink in, okay? So pretty much stating, look, what we have been doing over the last 30 years is drastically overblowing the impact of methane, if that methane came from near constant sources. But GWP 100 also does a poor job when you reduce methane, and you will see that in a minute. So that's what these colleagues from Oxford said. They developed a new unit called GWP star. Many of you have heard about it. GWP star is a unit or a matrix that actually uses in its algorithm GWP 100. But instead of just looking at one time point, GWP star looks at a rate of change over time for methane. Okay? So the years, let's say 1980 to 2000 to 2020, that would include 3 different time points, and methane during that time going up, staying stable, going down. That knowledge then, when using this new algorithm GWP star, will tell you whether that given source that produced the increasing, decreasing, or stable methane would have caused warming, no additional warming, or even cooling. So GWP star is a new matrix that's now amply published in the literature and also included in the most recent IPCC Intergovernmental Panel for Climate Change report. And not just that, the GWP star is not just discussed as a unit that better describes the warming impact of methane, but GWP 100 is now also significantly criticized, even in the last IPCC report. The first bullet point you see here, that GWP 100 overestimates the impact of the warming methane causes by constant sources by a factor of 3 to 4. That notion has now been cited in the last IPCC AI6 report. You see it copied here in chapter 7 on page 123. It says, and I quote, by expressing methane emissions as CO2 equivalent emissions using GWP 100, overstates the effect of constant methane emissions on global surface temperature by a factor of 3 to 4. So I think that this is really something you need to let sink in, okay? And as you can see on this page, GWP star is cited left, right, and center. So in my opinion, it is extremely important to, in addition of using GWP 100 when quantifying your industry's impact, that you also use GWP star, because without it, you will never know what your industry's impact is on warming. And you will never understand the nuances that I'm about to share in the next couple of slides. Before I do that, I want to just mention a brief difference between two of the main greenhouse gases that oftentimes are compared, and why they really shouldn't be compared and used, or a matrix being used to normalize them to one another. The first one is CO2 and how CO2 really accumulates in the atmosphere. Let's say you live 20 miles away from work, and on Monday, day one, you drive to work, you would put CO2 into the atmosphere. On Tuesday, you drive again, you put the same amount of CO2 into the atmosphere, which is now in addition to the existing stock from Monday. On Wednesday, you drive again, and you put new and additional CO2 into the atmosphere, new and additional to the existing stock from the day prior and the days prior, the week prior, the month prior, the decade prior, in addition to all the carbon your parents and grandparents put into the atmosphere, okay? So every time we burn fossil fuel, which is oil, coal, and gas, we add new and additional gas to the existing stock. Because of that, CO2 is called a stock gas, okay? Every time we burn fossil fuel, we add additional CO2 to the existing stock. Remember, CO2 is a stock gas. Currently, methane is treated when using GWP 100 as if it were a stock gas too, as if it were to accumulate just like methane does. But is that true? The answer to that is it's not true, because methane is not just produced but also destroyed. Methane is a flow gas, and if you have a constant source of methane, then an equal amount of methane that's produced is also being destroyed. This is a really important difference between these two gases. I will give you a quick analogy, okay? And I hope that you'll remember it and find it useful. The first analogy is one for CO2, and the second analogy is one for methane. And how these respective gases warm the planet is exemplified by this analogy. So the first one is the CO2 analogy. You have a bathtub. The bathtub has a faucet, but it has no drain. Every time you turn on the water with the faucet, whether you turn it on low, medium, or high, you add new additional water to the existing level, and as a result, the levels go up. The levels in your water bath can only go up because there's no drain, okay? No drain. The second bathtub analogy is the one for methane. Here you have a faucet, but you also have a drain, and the drain is always open. The drain is always open. If you turn the faucet on normal, then an equal amount of water that enters the bathtub is also extracted through the drain, meaning the water levels will stay stable. If you turn the faucet on low, but the drain is open, then the water levels will go down. And that's what happens when you reduce methane, okay? Warming can go down. Only if you crank that water faucet on all the way. Then you put more water into the bathtub, then you let go of through the open drain. And then levels can rise. And that is something that has happened for a long time and that needs to stop. Okay? That we add more methane than is being destroyed through natural processes, through this natural atmospheric removal that occurs. What we ideally want to get to is a point where we reduce methane, because then we reduce warming. Remember that, please. The next slide shows these three scenarios, namely an increasing methane scenario, a pretty stable scenario, and a decreasing scenario of methane over 30-year periods. How would these three scenarios, the increasing, the stable, and the decreasing methane scenario, be depicted by GWP 100, the old unit that has been used since 1990? GWP 100, because it ignores the atmospheric removal of methane, will predict that in all three cases, the increasing, the stable, and the decreasing methane scenario, we would add significant additional CO2 equivalent emissions to our atmosphere, causing new and additional warming. As I just said, GWP 100 is under fire, not the least by this group from Oxford that produced the GWP star matrix, the new one, which only agrees with GWP 100 in the first scenario, namely, when you increase methane by a lot, you are increasing a lot of warming. And that's the blue north of the x-axis. Increasing methane equals increasing warming to our planet. A pretty stable methane, or maybe slightly reducing over 30 years by 10%, will not cause any additional warming. You see no blue north of the x-axis. In fact, because you see a small decrease in here by 10%, you see some blue south of the x-axis and a negative sign in front of the number. And that means there's no additional warming in this case, but there's actually some negative warming. Some negative warming. Negative warming is a fancy word for cooling. If we slightly reduce methane, then we slightly reduce warming. We're taking carbon out of the atmosphere. But look what happens when you strongly reduce methane. And that can be done. We've seen it in different parts of the world, that animal manure emissions are reduced, or enteric emissions that are belched out are reduced. What happens when you reduce methane by a lot? Then you pull a lot of carbon from the atmosphere. Coming back to our analogy, this is like turning the faucet down. You reduce the inflow, and therefore, because your drain is open, you have levels going down. And that's exactly what happens when you reduce methane. And that is why I think methane is not a major problem, but is a major opportunity, because if we manage methane correctly, then we can have a really good bang for the buck, so to say, a really good reduction potential. One more slide that's kind of technical that I think is interesting. It compares and contrasts two greenhouse gases, namely CO2 and methane on top, from two sources. Let's say the CO2 came from a power plant, which over 30 years increases the amount of power produced. When you do that, when you increase power production, and therefore CO2 emissions, then look at the bottom, what happens to the related warming. That CO2 will cause an exponential increase of CO2, of the warming. So a linear increase of CO2 emissions causes an exponential increase in the warming. But let's say we have a feedlot with 10,000 cattle, we grow it to 15,000 cattle, that would increase methane over time. What would that do to warming? It would lead to a linear increase of the warming, not exponential, but linear. Now let's see what happens when you have constant emissions of these two sources, the power plant and the feedlot cattle. If you were to have constant emissions of CO2, that would still lead to increasing emissions of the related warming. Why increasing? Because of this, because of the fact that CO2 accumulates, and because it accumulates, every new molecule of CO2 causes additional warming. That's what we see here. So even constant emissions of CO2 cause additional warming. However, a constant source of methane, let's say a constant cattle herd, will not cause additional warming, but constant warming, no additional warming. This is compliant with the Paris Climate Accord. Constant amount of methane causes no additional warming, but constant warming from that methane source. But now look what happens when you reduce both CO2 and methane. Let's say our power plant example were one where over 30 years we reduced the CO2 emissions all the way until we shut down the power plant, and then it's at zero CO2 emissions. What happens with the related warming? Even though we are reducing CO2 emissions over time, the warming still goes up. Why? Because every new molecule of CO2 we put out there causes additional warming. And only at the point when we shut down that power plant, our related warming will go to and plateau. Okay, no additional warming, but only after you shut down that fossil fuel source altogether. That's what it takes to cause no additional warming from fossil fuel sources. You have to shut them down, and then you have a plateauing of the warming. Note the warming doesn't go down, it's just plateaus, okay, at that point. Now, what happens when you reduce methane is really miraculous. When you reduce methane, you're doing what I described with the bathtub. You are reducing the inflow, you keep the outflow constant, and that leads to reduced levels of warming. So this is what happens when we reduce methane emissions. So again, I do not want anybody to leave this meeting by saying, you know, Frank thinks that methane doesn't matter. Frank says in reality that reductions of methane will have a real instantaneous impact on warming, and that's a good thing. That means that our sectors, agriculture and forestry, are the two sectors out there in the whole of society that have the ability to actually be part of a climate solution. Not just can we be less of a problem, we can be part of a solution. So the question now, of course, will be, can we do this? Can we reduce methane and cause this effect here? Can we reduce a situation where we have a strong reduction of methane leading to what we see on the bottom right here? And the answer is yes, we can. Here in California, we have a new law that mandates a 40% reduction of methane, 40, to be achieved by the year 2030. The government decided to help farmers in achieving that goal and partnered financially in dairies covering their lagoons. You see that here. This is where the manure is normally stored. It's still stored in there, but now the lagoon is covered with tarp. And what you see bulging out here is biogas. 60%, 60 of this biogas, 60% of that biogas is methane. But instead of just burning that methane, they now take, to produce electricity, that is, they now take the biogas and they convert it into a fuel type for vehicles, for semi-trucks, for buses, and so on. And this conversion of dairy biogas to transportation fuels receives very high credits, credits that are so high that they almost amount to 50% of the income the dairy gets through the milk check. So very substantial financial support. The state considers this technology of covering the lagoons, putting in covered lagoons and transferring this biogas into transportation fuels as generating the most carbon negative fuel type there is. And that's a really good thing. And that is why it's considered a very positive pathway. It has led to 2.2 million metric ton reductions of greenhouse gases, which equates to a 25% reduction of methane from our dairy sector in California. And California has a very vibrant dairy industry, very strong dairy industry. For this to have happened, a 25% reduction in 3 or 4 years is miraculous. And it will continue until we are at 40% and beyond that. And by the way, if you do what I just say, you reduce methane by a lot, you induce this negative warming, meaning a cooling effect on the methane side, and that can offset nitrous oxide and CO2, leading that sector, in this case, the California dairy sector, to become climate neutral. Climate neutral, meaning not adding any more additional warming to our planet. For those of you who are visual thinkers, you see here a fuel station where renewable natural gas from the dairies is put into semi-trucks to fuel semi-trucks and replace diesel. So they no longer get diesel, they now get renewable natural gas that originated on dairies. In addition to the reductions of emissions from lagoons, we also reduce emissions from enteric sources, meaning the belching. We have done a lot of research here at UC Davis on feeding various feed additives that have the significant potential to strongly reduce enteric methane. And I think within the next 5 years, we will see many of these additives showing up in the feed stores so that our producers can make use of those and reduce enteric methane as well. I do believe that our livestock sector can become an important part to a climate solution. I think we need to stop thinking of methane as a liability and start thinking of methane as an opportunity that, if we manage it correctly, can really get us on the other side of the climate agenda. With that, I want to close my talk and just point out that I am on the clear.ucdavis.edu website. I have blogs there, explainers, and so on. So please come and visit us there. And now I'm happy to turn it over to you and then have our question and answers at some point. Thank you very much for your attention.
Thanks a lot, Professor Mitloehner. Very interesting, very provocative, very original. Cicero, floor is yours.
Okay, okay, thank you guys, thank you, Professor Mitloehner. So I try to present in 5-10 minutes. It's difficult to present after Professor Frank, but I try to do my best. So let's share my screen. Okay, so this is a product that we are developing in our observatory. So we have been studying these methane emissions in the livestock sector in the last year. And also we are preparing some reports, and this is the first part of this report that we are studying the methane emissions and how these how different types of technology could be applied in the livestock sector in Brazil to achieve this methane mitigation. And also how Professor Mitloehner already showed how you can convert these emissions in opportunity in the future. And also these other colleagues, Talita, Camila, and also we have both Eduardo's in our team. And I put this provocative title, Chasing the Methane, also the Brazilian case. And we have, in this first product, we have this roadmap, but of course I'm not present all this content. I'd like to show just some results here in topic 5. That's for the Brazilian case. And of course, Professor Mitloehner already present how this new metric, the GWP star, could change how we understand these methane emissions. So it's already, we got this picture from this figure from also a publication from Professor Mitloehner. So I already, I jumped this. And of course, this is our attention here is to focus on the new metric, the GWP star. And I would like just to highlight this is the formula of conversion of GWP 100 to GWP star. And we are also, of course, as Professor Frank mentioned, we are considering the emissions that we have today, and also we are considering the emissions that we have 20 years in the past 20 years, because we are considering all this flow from the methane in the atmosphere. So when you look at the Brazilian livestock emissions, this is the emissions from the enteric fermentation in different metrics. And I'd like to show to you guys here today that this red line here is our livestock herd. You can see that in 2020 we have more than 200 million heads of animals, and this is just for beef production. Here we are not considering the dairy animals, and also, of course, all of you are aware about this. These animals are in the pastures. We have feedlots, but it's a small share compared to the beef production that we have in Brazil. And when we considering these methane emissions and the conversion in different metrics, you can see here on the right for the year 2020, you can have several different numbers based on the warming effect that we are considering different metrics. And the most common and we are using in the IPCC and also for the national inventory for greenhouse gas emissions in Brazil, we are using GWP 100, and you can see for 2020 you have around 300 million tons of CO2 equivalent emission. But now, when you look at this blue line here, that is the new metric, GWP star, is showing a different story about the methane emissions in Brazil. And also, you can see here, of course, we don't have the first 20 years because we are considering this cycle. And we are starting 1980, and you can see, as already Professor Frank showed us, that we have, if you are increasing the emissions, of course, you are increasing the warming effect under this metric, but also if you have a slightly change in methane emissions, this metric could show a decrease in the methane emissions, as we can show here, and also under this new metric we have a slightly higher value for the greenhouse gas emissions for livestock. And in this first product that we are we produce some very simple scenarios for the herd size in Brazil. Of course, we are not considering the costs in this first version. Of course, this is a thing that we are studying and we are developing now, but this is just a provocative scenarios that we can show how the herd size matters, and also the metrics of conversion matters in these scenarios. So as you can see here, for example, in the baseline scenario, this is for the metric GWP 100. Our baseline scenario is considering the historical trend for the herd size, and we are considering this challenge scenario that we are considering an increased herd in the future, meaning that we have more challenges to mitigate these methane emissions. And also we are considering an alternative scenario that we are calling conservative scenario, that we are considering that the herd size will could decrease, and also a lot of low carbon technologies applied to livestock production has this result that we can increase the live weight gain during the beef production. And of course, if you have more live weight gain, you can have a short period to slaughter this animal and convert in beef production. And the result, in the end of the day, you have a lower herd size and you have a higher productivity compared to in a scenario that we have a stable productivity. So, and of course, you have different levels of GHG emissions with this metric. And when we considering the baseline scenario, but now with the GWP star, you can see that in 2050, we are showing a half of emissions compared to GWP 100 if you have a stable herd size in Brazil. And this means that we are going back to the level of emissions in 2080. So when you put back in this original curve. And of course, if you have a scenario that we have more challenge to to apply these low carbon technologies, of course, GWP star shows a higher level of warming effects from this production. And on the other hand, this is also a provocative scenario. So, and when you look at the conservative scenario, where you have this decreasing in the herd size, you can see that in, I'd like to highlight here, in 2040, you can achieve the climate neutrality. Means that we are not we don't have a contribution from the livestock production to the warming the planet. So as Professor Frank already mentioned, so and also this is an interesting result that we are showing in this study. Of course, we have these numbers for the herd size in each scenario, in the baseline, and also I'd like to show here the CO2 warming effects under the GWP star, that you can show this, how can I achieve and this huge decrease in the warming effect. And of course, this we can apply this to have a measure of the carbon footprint for the beef production. And also in this table here, I'd like just to show that when you apply different metrics, we can change the story that we are showing from the livestock production. And you can see here, for example, here the kilograms of CO2 equivalent per kilograms of beef production under the GWP star. This is just the historical trend for in Brazil. You can see here we have around 7 kilos of CO2 equivalent emissions per kilograms of beef. And when you look at the same data, but considering the GWP star, we can see a higher level, but this is decreasing a lot in the last 10 years. So from 12 kilos of CO2 warming effects to 9, and if you project this for the future, we can expect a huge decrease from below 9 kilos of CO2 warming effects per beef. So this is just some final thoughts. Of course, we are showing here that the animal diet, all these technologies, the management, biodigesters, as already Professor Frank showed, also the animal diet and the health matter. And the idea here that we are studying is that we can increase the live weight gain and also reduce the slaughter time, and we can reduce the herd size in Brazil, and this we can achieve this with these low carbon technologies. And of course, the metric, the GWP 100 and GWP star, both have limitations, but also when we considering for the policy perspective, this matters, and we can deep our understanding these metrics. And of course, this is that I have for today, and of course I'm happy to comments and ideas in this presentation. Thank you guys.
Thank you, Cicero. So now the idea is to open the floor for question and answers. I'm not sure if Angelo, are you willing to make a question? I don't know if that's part of the planning. Otherwise, I'll jumpstart.
Yes, can you hear me?
Yes, we can.
Yeah, I'm just on transit here, so it's quite hard to follow. But anyway, I think it's a wonderful presentation that we had from Professor Frank, and really elucidating those things. And it's quite astonishing that all the community studying methane hasn't got at that level of understanding about this anthropogenic, biogenic methane emissions. So one question that I would like to ask. It's about those chemical reactions that could degrade the methane in the atmosphere. So are they going to be there forever, or the amount of the sink they are, the amount of methane they can reduce per year is going to change in the future because of climate change or human actions, or we can be sure that it's going to be forever there? We can rely on that as one source to degrade methane through time. I think it's my main first question. A second question that I have is that my perception is that we can burn methane to produce energy, and it will get methane back to CO2. But if CO2 accumulates, isn't it better to keep that as a methane? That since methane has a biological sink cycle? So those are my two questions.
So maybe the second question first. So the question of, shall we burn methane because then it becomes CO2 again? The carbon that's in the methane that we end up burning is not new carbon, okay? This carbon came from CO2, as I showed in the biogenic carbon cycle, okay? So you have atmospheric CO2 that is the origin with respect to carbon for the methane. And so when you burn CO2, when you burn CH4, methane, then it becomes again what it used to be before. So that's a wash. So the reason why this matters is, so just think of the CO2 that you exhale right now, that you and I exhale right now. Why is that CO2 not considered additional emissions, even though all these people in the world exhale all the time? The reason why it's not counted is because what we are exhaling, the carbon that we are exhaling, was previously in plants that we ate, and before, while these plants were still alive, they sucked carbon out of the air. That's why it's not considered a net additional carbon. But the same is pretty much true for the biogenic methane. You have atmospheric CO2 that becomes methane for a while, but then it becomes CO2 again. That's not additional carbon. Just one, really quickly, the first part of your question was just one keyword to trigger my memory. The first part.
About the chemical reactions that degrade methane.
Yeah. So this is actually a super interesting question. Because the chemicals that do this, that pretty much kill the methane, are the so-called hydroxyl radicals. And these hydroxyl radicals are very abundant in the atmosphere. They are very short-lived, okay? When a hydroxyl radical is in the atmosphere, it lives there for seconds. And now comes what's really exciting or interesting. Have you ever seen a map generated by NASA that shows global methane clouds over different regions in the world? And if you have, you might have been surprised that you see certain areas in the world that light up in red and others that don't. And those areas that don't oftentimes are the ones where you would expect methane, but you don't see very much. So many people have asked themselves for the longest time, why do we see those methane clouds in some parts of the world, but not in others? The answer is that those hydroxyl radicals don't just kill methane. In fact, they have something else they like to oxidize more than methane, and that is carbon monoxide, CO. When you have a region that produces both carbon monoxide and methane, then the hydroxyl radicals will preferably take on the carbon monoxide and leave the methane alone. And in those areas, you see very large methane clouds. For example, in China, they have a lot of combustion and therefore a lot of carbon monoxide, and they also have a lot of methane. As a result, they have large methane plumes over their country. Same is true for northern India. In the United States, you see relatively little methane. You see some methane clouds over the Dakotas, and you see some in West Texas, but you don't see much in the rest of the country. It has a lot to do with the question you're asking, namely, what happens with these hydroxyl radicals? What do they preferentially oxidize and where? The picture around methane is even more complicated, much more complicated than what I just presented to you, because we haven't even considered that issue of which region produced both carbon monoxide and methane. Most of the regions that only produce the one and not the others don't have visible methane problems. I'm sorry, that was a long answer, but a very important question.
Wonderful. Thank you very much, Professor Frank. Daniel, if I may, I would like just to ask, so when do you think the world will wake up to this new metric of methane, right? So do you think that is going to become a consensus soon, since the science, the logic is there, and from your presentation, I don't have any doubt that we should be doing this new metric instead of the old GWP 100 and so on?
So in my opinion, the best way of quantifying greenhouse gases is by quantifying them separately. Methane separately from nitrous oxide, separately from CO2. Why? Because these are very different gases. Methane and nitrous oxide, methane and CO2 have really nothing in common. The dynamics of how they warm is so different. Just remember that one line graph I showed you. Okay, if you increase CO2 versus you increase methane, and then both are constant, both go down, they have a totally different impact on climate. You should not just put them into a matrix if you can help it. But if you must put them into a matrix, then I would recommend GWP star. However, while saying that, most of the world uses GWP 100. You cannot get away from it. You have to do that too. In my opinion, if I were in a leadership position in a country, I would use both GWP 100 and GWP star.
So I have two questions. One actually is connected to your argument about the dynamics of warming. So if I understand well, it seems to me that the amount of time it takes for the methane to be degraded in the atmosphere matters for the calculation. So usually we take the time frame of 10 to 12 years, but it might take longer, as you're explaining, if I understand well, in China, for example. So, or it might take less time. So would it make sense then to think of strategies to accelerate the process of burning or degrading the methane, or considering whether a particular area has more monoxide, carbon monoxide, into the calculation, instead of just taking it, ignoring the time that it takes for the methane to be degraded, because it doesn't seem to me that that variation is being taken into account by the current metrics. So that's
it's not at all. Yeah, it's not at all taken into consideration. It complicates things even further. So I'm even hesitant to bring it up because that really complicates things, okay? And it makes several countries in the world look as if they're having bigger problems, even though they're receiving some of the emissions from other countries that cause the atmospheric dynamics to unleash over their respective areas. So it makes things much more complicated. And I don't really see how we can incorporate that into any kind of calculations. But the truth remains, if you take a look at satellite images, and they are now available for the world, okay, I can send them to you. These are videos of satellites that have methane sensors, and you can see where in the world you have those plumes. They are particularly strong in West Africa. They are particularly strong in northern India. They are particularly strong, and the strongest in the world by far, in China. And then you can do the same thing with CO. You can look at where CO is generated, and then you can look at both, and you will see that what I just said is true. But how do you account for all of that? I mean, politically, and make it fair. It's difficult. It's very difficult. There's also something else that I want to bring to your attention. It is the topic of territorial emissions. Territorial emissions. What that means is something that most people are not aware of, namely, that emissions internationally are counted to the place where they are put into the atmosphere. So, for example, if you are Norway, the country of Norway, then you are a strong producer of fossil fuels. Oil, coal, and gas are extracted in Norway, but they don't burn those fossil fuels in Norway. They send them to other countries, and then these other countries, for example, Germany or the United Kingdom, they burn those fossil fuels and are blamed for the emissions from that fossil fuel. Not Norway, but Germany and the UK, because that's where the fossil fuels are burned. If you were not a fossil fuel exporting nation, but an agricultural nation, like Ireland or New Zealand or Brazil, then the emissions of the food that you produce are blamed to you, because the emissions are generated, in the minds of these folks, in your country by cows belching, by manure decomposing, and so on. And so it's now not the countries that import the food that you produce that are blamed. They don't even receive a partial blame, but you, the producing agriculture country, receive all the blame, okay? All the blame. So that means Norway looks clean as a whistle because they're exporting all of their fossil fuels to other places. But Ireland, exporting 70% of their agricultural goods to other countries, receive the full blame of producing that food in Ireland. This has always been a question of fairness. It has never been resolved. If I were a Brazilian, I would definitely look into that issue, because that is of huge importance to you, because agriculture produces at least a third of your greenhouse gases as a nation. And you take the blame, and not even partially those who import the goods that you produce.
That's very interesting. So I have a second question, but I'd like to invite Bruno. He's been on the queue, and then if we have time, I make my question later. Bruno, thanks.
Hi, can you hear me?
Yes.
Yeah, thank you. So Professor Frank, thank you a lot for your presentation. It was very clear. Even I'm an economist. I have very few background on this kind of issue, and it was quite clear to understand your argument, and it seems totally logical. So I don't know the discussions about the more detailed discussions, but it seems totally logical. And I'd like to make a question, firstly, that relates to what you said about separating the greenhouse gases, thinking about methane in a way and carbon dioxide in other way. In Brazil, I think the main technology we have here in order to do what you are saying to reduce the emissions in the cattle sector, it's the integrated system we call integrated cattle forest feedstock that we have here. And I think there's a problem here to make this the separation of gases, because the logic of the system would be to use the forest or the crops in order to compensate the methane. So we are talking about a relation of units of carbon dioxide that you are capturing in the plant process with the methane that you are emitting in the feed process. So my question is that easy to do, this kind of separation, and the relation, the how can I say, not the compatibility, but we have these numbers very clear in order to make these comparisons, to make this kind of thing. So that would be
So if you have the inventories for the different gases separated, then you can do calculations as to how the CO2 that your farms or ranches emit, how that warms the planet. Then a separate one, how the methane that you emit, how that warms the planet. And the third one, how the nitrous oxide does it. And then, so you look at sources and you look at sinks. Really important, you look at sources and you look at sinks. For CO2 and nitrous oxide, you don't need to look at sinks. But for methane, you do need to look at sinks, because the hydroxyl oxidation is a big deal, obviously. And so you would by doing so, have 3 calculations on how the 3 respective gases warm the planet. And you could then do an integration of those and find out whether or not you are at a point where you have reached climate neutrality, which is not no impact on warming, but it is no additional impact on warming, because you still have an impact on warming, but no additional impact on warming. That is reaching the point of climate neutrality. if you go one step further beyond climate neutrality, if you reduce methane stronger than what you need to offset nitrous oxide and CO2, then you actually get to a point where you can sell your credits to other industries that cannot reduce their emissions, like the fossil fuel sector. They cannot net reduce emissions and induce cooling. They cannot do that. So they will have to buy your credits, and they will buy your credits. So if your methane reduction is strong enough, you will be able to sell carbon credits to others. And so that to me is also very exciting to me. And I want to re-emphasize that the whole climate picture for animal agriculture has more opportunities than challenges in it if we manage it correctly, particularly methane.
Thank you.
Thanks a lot, Mario.
Thank you. Can you hear me?
Yes.
Okay. So thank you, Professor Mitloehner, for your presentation. It was really breathtaking to know that there are new metrics to measure correctly methane emissions. And thank you, Cicero, also for highlighting how our livestock sector here, the picture changes due to these new metrics. Now, I was wondering here, and related to Bruno's question, whether or not the system of production matters to impacting, methane emissions. So, for instance, if you are a producer who produces in a confined system, then you are able, of course, to put the manure together. You can have a biodigester, etc. But if you are a pasture-based system, then of course it's much harder to do that, not impossible. So how is that taken into account? That would be my question. And how does that change the picture of methane emissions? Thank you.
So I assume that you're all familiar with how the US beef system works, right? You have 750,000 ranches in the United States. Each ranch has on average 50 mama cows. 750,000 ranches, and then there are 1,400 feedlots. And most of the cattle in the United States are finished in feedlots. So they spent the last 4 or so months in a feedlot. If you look at the whole beef supply chain from cow-calf over stocker to feedlot, then the cow-calf animals on pasture make up about 80%, 80, of total greenhouse gases from the beef supply chain. The feedlot sector makes up only 10%, because the diet these animals are fed is high in concentrate and not in roughage. So the diet that these animals eat doesn't lend itself to a lot of methane. In fact, it's that fact, along with the efficiency, that does not put the crosshair on the forehead of the feedlot industry. The problem you are mentioning is real, namely, how do we get grazing animals to reduce greenhouse gases? When indeed we know that the roughage in what they eat is driving particularly methane. And the fact that we can't really get to those animals day in, day out. We don't feed them ourselves. They just feed themselves. And so there is now a lot of research going on finding ways to either get some active ingredients from feed additives into salt licks where animals go frequently, and then normally they just lick their minerals, but now also in addition to the minerals, some active ingredient to reduce methane. Either that, or into drinking water, or into a form of a bolus that you put into the animal's digestive system, where it slowly releases its active ingredient to mitigate methane. The New Zealanders are also working on a vaccine for methane, but how far that is, I don't know. So it is much more difficult to reduce methane using feed additives on pasture, and it's impossible to reduce the methane from the manure, because obviously the manure is just falling off the animal and working its way into the ground. What is possible, however, is that your animals over time become much more efficient, or that you improve the reproductive rate. That has a huge impact on emissions. So if you increase your reproductive rate by 20% or so, then that means you have less animals that are not getting pregnant, and that means that has a significant impact on herd-wide emissions. So performance, reproduction, health of animals, all of that impacts emissions as well, as we all know. The question is, how can we get this knowledge into the heads of people who regulate us? Because they seem to think that only a reduction of direct emissions is a real reduction. That's not true. That is not true. For example, in the United States, we used to have 25 million dairy cows. Not too long ago, 25 million. Today we have 9 million dairy cows. We went from 25 to 9, but with this much smaller herd today, we are producing 60% more milk. We have reduced the carbon footprint by 2/3 by going from 25 to 9 million dairy cows. They are producing, the much fewer animals produce way more milk, and the environmental footprint has gone down drastically. You would have to be a fool to say it doesn't matter that performances have improved. Of course it matters. It matters profoundly. But we have not done a good job in agriculture explaining why that matters. I tell you this, if you want to explain that to politicians, then you need to use analogies they understand. For example, when it comes to, let's say, feed efficiencies, okay, and how feed efficiencies affect emissions, then if you just say that to a politician, their eyes just roll and they will not understand what you're saying. But if you're saying, look, you're driving a car today, and the car you drive today is undoubtedly more fuel efficient than the car your parents drove, and definitely more than the car your grandparents drove. All three cars were able to drive 100 kilometers, but you are doing that today with half the amount of gas burned than your parents' car, and maybe 2/3 less gas than your grandparents' car. And by burning less gas, you're putting fewer emissions into the air. Believe it or not, the same is true for cows. A more efficient cow is a cow that emits less. If we have more productive herds, we are emitting less. It's not just a question of feeding something to animals that's an additive or using some fancy technology, but if we improve performance of our herds, we reduce environmental footprints.
Thank you. Thank you.
Very interesting. Let me add another question here. Your last point, if I understand well, Professor Mitloehner, suggests that we should focus on, increasing the productivity and efficiency of cattle production, and by doing that, we're also contributing to the environment. But I have often heard you stressing the unique importance of cattle to open new areas of the world to the human nutrition system. So only 1/4 of the world is actually ready for agriculture. And that means that cattle has a unique importance in actually opening the ground for human life. But then that also suggests that we will probably need to increase the number of animals that will actually be produced in the world if we want to feed the world. I'm not sure you would agree with that, but then the question is, would this new way in which we're calculating emissions, and especially the burden of warming that the cattle actually has, wouldn't we be actually imposing an extra weight or extra burden on cattle vis-a-vis fossil fuels? So my question is might not be clear, but let me add here, then probably you get the point. So according to this new way of actually quantifying emissions, if we reduce emissions, then we have a very important credit, a very important actually source of resources. But the opposite is also true. In other words, if we increase the number of animals, then the burden will be very high. And I understand that as saying no more cows. I mean, just what you have. How would you actually interpret that?
So first of all, I want to be very clear. GWP star is not a get out of jail free card. Okay, it's not at all that. It is a matrix that pays really close attention to the fact that this gas is not just produced but also destroyed. If you add additional methane by growing herds, then you add additional warming beyond what is predicted with GWP 100. So if your emissions go up, then GWP star is a matrix that makes you look worse, not better. However, if you either stay constant with your methane or preferably go down, then you will see, and Cicero's graph showed that very nicely, then you will see that your trajectory is going down to a point where you reach climate neutrality. So if your goal is to have an industry that at some point in the future becomes climate neutral, meaning adding no additional warming to our planet through the use of beef production in Brazil, if that is your goal, then you need to have a matrix that is fit for purpose. And that means a matrix that can show the rate of change over time. GWP star can do that. GWP 100 will never do it. If you look at Cicero's data on GWP 100, then you show me where along that trajectory you will reach climate neutrality. You will not find it. You will never get there. It's not possible. No matter what you do, no matter how hard you try, you will never reach climate neutrality. And so that is very frustrating to people, okay? So what I do with producers here in North America is I tell them, because public policy is set according to GWP 100, and that won't change anytime soon, use GWP star in addition, and show the different powers to be that because your goal is to reach climate neutrality as a sector, you need to have a unit that allows you to predict that point, okay? Because that is your goal and that's society's goal, okay? The Paris Climate Accord has the goal of not adding additional warming. So let's use a unit that allows us to predict no additional warming. GWP 100 is not that unit. And the IPCC, just said that in their AR6 report. I showed you the copy of the page. If you have a constant source of this gas, then you are not causing additional warming. And if you are using this old matrix, you are overblowing the impact of your industry by a factor of 3 to 4. So in my opinion, it is really important that we clearly define as to what our goals are. In my opinion, the goal should be climate neutrality, and then develop milestones as to how we can get there and verify that. Okay, it's really important to be careful about this. You do not want to make promises you can't keep. Otherwise, your critics will call you, they will accuse you of greenwashing and of creative accounting, using a unit that best serves your purpose, okay? And this is not what this is about. This is about finding the best scientific tool to describe our path to a point of climate neutrality. Okay, that's what it's all about. Now, you have several challenges in Brazil. The one challenge is that in some parts of Brazil, a sink is taking off, okay? By taking, you mentioned it at the beginning when you introduced me, by taking some trees out and so on, you're taking a sink of greenhouse gases out. If you then put cattle there instead, then you are replacing a sink with a source of greenhouse gases. And that is in the international accounting what gives you the black eye in Brazil. Whether I agree with that or not is not the question, but this is how the rest of the world views Brazil right now. And the other thing is that I think is really important for you. You need to get a really good handle as to how the land that you're using for beef sequesters carbon. In other words, you need to know more about the sinks around greenhouse gases and beef. You need to know how productive can these sinks that we have be in sequestering carbon. That's your soils, your vegetation. But then you also need to know there are some sinks that are taken away, some trees that are taken away. And you need to do you need to do the accounting for that. This will be really important to you. I'm afraid if you grow herds, then regardless of which matrix you use, how you calculate it, your impacts will go up. And it will not go down unnoticed. People are focusing right now, particularly your competitors are focusing on Brazil. Unfortunately, I think that's very unjust, but it is happening.
Cicero, we have 2 minutes, very quickly.
Yeah, I have. My question is about this last comment from Professor Frank. So I think that we have some strong words here, like the livestock is a part of problems or is a part of solution. And this is and how we can apply these metrics to change the narrative. For example, a lot of when we read the news here in Brazil about changed diets, so the whole sector is, oh my God, we are going to change the diets. This is very bad for the whole sector. Okay, this is true for a rich country, but in Brazil, when we have these income chains, of course, the poor people wants to eat more beef. So this is not a reality for Brazil. So, but this is reality for Europe, for US or other countries. So exactly the countries that our beef exports are going. So, and also this is my question. My question is about this. How this narrative, this diet change, this news, how we can show them that the livestock is now a part of solution, is not a part of problem. How is your perspective on that, Professor?
So I wouldn't say livestock is part of a solution. The way I word that in front of the public is a reduction of methane is part of a solution. Okay, so I don't tell them cows can cool the planet. Okay, I'm not saying that. What I'm saying is we in agriculture understand that climate change is a significant problem. We are not a major contributor, but we are a contributor. We know how much we contribute, and we have set goals to reduce our impact. And if we succeed in reducing our impact, if we, for example, reduce methane, we reduce warming, and that makes us part of a climate solution. That's how I word that, and that's a very important distinction. So don't say cattle are part of a climate solution, but say we, the cattle industry, understand our contribution. We know that methane is one of the significant contributors. If we manage methane right, then that methane reduction can have short-term impacts on climate, and we are committed to making those impacts possible. That is how I would word that. And this is how you can get even the critics to agree with you. So with respect to consumption of animal source foods, we do not see that in the United States. We have strong demand for animal source foods, and that includes all animal source foods. The plant-based alternatives in the United States, the Impossible Burger and so on, they are tiny, 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 and they stay that way. Their growth has stopped. Where I do see, however, some changes, that's in parts of Europe. For example, Germany, where I'm originally from. There I see that there is a move to a more plant-based diet. I see more people becoming flexitarians, reducing their consumption of animal source foods. I do see it there. I hope it won't happen in North America, but it could. But I don't see it in South America. And I also don't see it in your export markets, definitely not in China, where consumption of particularly beef is going skyrocket high. Same is true for Northern Africa, where also part of your beef goes to.
So thanks a lot, Professor Frank Mitloehner. Thanks, Cicero, for your presentation as well. Thanks for all of you guys that stayed with us here until the very end. So I'm going to end very quickly, but thanks a lot. This was very instructive, very provocative, and it just excites us to actually go back to research and deepen our analysis and think about new areas and new possibilities of contributing to what's going on in the country and in the global debate. And whenever you come to Brazil, please let us know. It would be wonderful to host you here at FGV, Getúlio Vargas Foundation, and eventually in one of our trips to the US, maybe we meet over there as well. Thanks a lot.
Please do.
Thank you.
I appreciate the opportunity a lot, and I hope that we stay connected. I would really enjoy that. Thank you.
Thank you.
Thank you.
Bye-bye.
Bye-bye.
Bye-bye.